So, hello to everyone. It's a pleasure to present my work here. Very nice series of seminar. I'd like to thank the organizer for this focus week and also for the previous series of seminar, which I really enjoyed in the past month. I learned a lot from all of them. They will present my work made in collaboration with Ale Cantipin, Francesco Sannino, Xu Wang, and Chen Zheng. In particular, I will talk about Doan symmetric conformal field theory between 4 and 6 dimensions, and I will discuss in particular how to use the large charge expansion to test a proposal dual description of this CFT. So the model we're talking about is the usual factor for Doan theory, which we consider for the moment in d dimensions with the Lagrangian given in the slide. As we all know, there are strong evidence, so experimental, for the existence of an infrared fixed point between 2 and 4 dimensions. In particular, just below 4 dimensions, this CFT is weakly coupled. In fact, if we consider the model in 4 minus epsilon dimensions, the fixed point coupling is proportional to epsilon, up to correlation of order epsilon square perturbatively. This theory is very important for physics, for real-world application. In fact, in 3 dimensions, it describes phase transition, the critical behavior, a lot of real-world systems as superfluids, superconductors, easy plane magnets, all the system which falls into an universal class. What happens instead if we change the number of spacetime dimensions and we move above 4 dimensions? In this case, this is an interesting case because the quartic interaction becomes RG relevant, becomes non-renormalizable. As a consequence, in the infrared, we have a free field theory. On the other hand, one can study this model, even if non-perturbatively, is perturbatively non-renormalizable, being the 5 to the 4 interaction irrelevant, but one can study this model using the 1/n expansion. And has been shown that at least a large n in the 1/n expansion, this model have a free infrared, but on the other hand, in the ultraviolet, it flows to an interacting fixed point. And the presence of this interacting fixed point, as was shown first already by Parisi in the 75, makes the theory renormalizable order by order in the 1/n expansion. So we focus also in the range between 4 and 6 dimensions, where this fixed point may be unitarity. Why we stop in 6 dimensions is because if we consider the scaling dimension of the phi I operator, this is 2 plus order 1/n correction in every D. So above 6 dimension, it violates the unitarity bound. The intrinsic range where the ultraviolet fixed point may exist and be a unitary, described by unitary theory, is between 4 and 6 dimensions. This is interesting also because it provides an example of a non-supersymmetric 5-dimensional CFT, which may be of relevance for holography. In fact, it's believed the ON model in D dimension has an holographic dual in terms of Eiger-spin theories on ADA space in D+1 dimensions. On the other hand, even if the 1/n expansion show the presence of this fixed point, there are various results already starting from 81 about the fact that we cannot have a true critical behavior in Doan theory above 4 dimensions. So the solution to this small puzzle is that this ultraviolet fixed point is unstable and is actually metastable thanks to the stability as we enlarge the value of n. This has been analyzed in the paper showing in the slide, where SB point out that this instability is realized actually by instantonic effects, which what these instantons do is to give an imaginary part to the CFT data of my theory, of the ON theory between 4 and 6 dimensions. So this ultraviolet fixed point is actually what can be called a complex CFT. On the other hand, since instantons are suppressed a very large value of n, when n is large enough such that the imaginary part of the CFT data is numerically negligible, this fixed point can be filled as a real fixed point, and the theory can be studied, for instance, with a conformal Bourset, as has been done in the paper showing the slide. There is a conjecture about the quartic CFT, ultraviolet CFT between 4 and 6 dimensions, which has been proposed first by Fei, John, Klebanov in 2014. And the conjecture is that this ultraviolet CFT is equivalent to the infrared fixed point of the cubic, of what I will call the cubic model described by the Lagrangian in the slide. This is a model with ON symmetry. Again, it has n+1 fields, so it has a ON vector plus a singlet field, eta, which interact with cubic interactions, and we refer to this theory as the cubic model. This conjecture, this postulate equivalence between the two fixed points, is also interested because this last theory is weakly coupled just below 6 dimensions, so can be studied, for instance, in d equals 6 minus epsilon using the epsilon expansion. And we have access in this way to a weakly coupled description of what would be otherwise a strongly coupled theory. One can compute the beta function of this model in the epsilon expansion, and has been found that for above a critical value of n, which is has been estimated to be around 400 through the latter results, which make use of phi loop beta function and Padé approximant. And above this critical value exists this infrared fixed point, which is believed to be dual to the ultraviolet fixed point of the quartic model, with the fixed point values, 2 couplings shown in the slide. This conjecture has been proposed as support to the showing that the various CFT data, carrying dimension or peak coefficients, take the same value in the two theories. Here we have to pay a little bit of attention, since one theory is usually the quartic model is studied through the 1/n expansion, while the other theory is usually studied using the epsilon expansion, so the comparison is made at the level of terms which overlaps between the two expansions. If there is any question, just stop me at any time. So we can consider fixed charge operators inside this theory. In particular, the quantity we'll be interested here is the scaling, what they call delta Q, so the scaling dimension of the lowest lying operator with total charge Q. As we show, this operator, to identify them, are the operator with classical scaling dimension Q and transform in the traceless symmetric ON representations, which can be depicted pictorially as a Young tableau with Q boxes in just one row. For instance, for Q equal 1, the operator is the phi I fields itself, the n vector. For Q equal 2, we have the usual 2-index traceless symmetric ON tensor. And as a physical meaning, related to maybe the question has been made before, how we may measure the scaling dimensions. As a physical meaning, this operator in general represents anisotropic perturbations to an invariant system. And the scaling dimension defines what is called in condensed matter crossover critical exponent, which measures the stability of an invariant system against anisotropic perturbation. For instance, we can have a Heisenberg magnets and ask how the crystal structure of the magnets perturbs critical behavior. And this is measured by this quantity. So for the scaling dimension of the charge operators. The study of these operators in this theory is quite recent. There are in particular two papers, both from 2020, one by Arias Tamargo, Rodriguez Gomez, and Russo, which computed this delta Q, the scaling dimension, and they show that the contribution coming from the exponential of all the Feynman diagrams with the leading charge scaling at every loop order give the same results in both theories. And this is the results shown in the slide, where 2Q is the classical scaling dimension, and the second factor is the anomalous dimension to leading order in epsilon and in the charge. At the same time, has been another interesting results by Simone Giombi and Jonah Hyman, again in 2020, which compute delta Q in arbitrary dimensions, considering the double scaling limit where you take n going to infinity, the charge going to infinity, and they keep fixed their ratio, Q over n. In this case, the scaling dimension can be computed in the expansion shown in the slide as a 1 over n expansion, where every coefficient function fk depends only on the combination q over n, only on j. In particular, in this paper, Giombi Hyman compute the leading order in this expansion, f-1, which will be the results will be interesting in our work. Another interesting fact point out by this series of paper is that in the first papers we showed that in this case instantons, which give rise to imaginary part to the CFD data, in the large charge regime are suppressed exponentially as e to the minus q. So one can wonder if the suppression is such that the large charge sector of this theory is stable and can be, for instance, have application in holography. The answer has been found to be no, because studying the quartic model in the double scaling limit considered before has been shown that exists a critical value of the charge, such that above this critical value, the scaling dimensions acquire a non-trivial imaginary part and become complex. This has been studied in details, always in this paper by Giombi Hyman, 2020. And here I report the result, where they numerically estimate this value of the critical charge at the leading order in this double scaling limit. This value of the critical charge depends non-trivially on both n and the number of spacetime dimension, and this is the result. As we can see, for near 4 dimension and 6 dimension, where the quartic and the cubic model becomes respectively free, the critical value of the charge goes to infinity. So this is where our work collocates. We wanted to know more about this equivalence between the cubic and the quartic description, about the complex scaling dimensions. So we proceed in a complementary direction by studying directly the cubic model at large charge in d equals 6 minus epsilon dimensions, and considering this other scaling limit, when one take epsilon going to 0, q going to infinity, and keep fixed the product q times epsilon. In this case, our scaling dimension of fixed charge operators can be computed, in this expansion, so as an expansion in 1 over q, in 1 of the charge, in the inverse power of the charge, where every coefficient functions depend only on the product q times epsilon, which is kept fixed. In particular, we computed delta -1 and delta 0, and we compare the results with the no large n results in the quartic theory. How this comparison is performed in practice: on the cubic side, we consider this double scaling limit. We have this expansion for the scaling dimension. On the quartic side, we have the results of John B. Hyman, which consider this other scaling limit. And so they compute delta Q according to this other expansion scheme. And we analyze the terms which overlaps between the two expansions. In particular, there are two infinite series of terms which can be compared using the results available. These are all the terms scaling as Q times Q to the epsilon over n to the j for the integers j bigger than 0. And this term, if the conjectured dual description holds, I expect to match between delta minus 1, the leading order of our expansion, and f minus 1. At the same time, all the terms with we can compare also the whole series of terms scaling as q times epsilon over n to the j for all the integers power j bigger than 0, which I expect to match between delta 0 and f minus 1. I will not go through the detail of the computations, which in general follow previous computation made recently. In particular, by usual mean, we use the state of operator correspondence. We map our theory on the cylinder, and we compute delta Q in a semi-classical expansion around the ground state at fixed charge. Furthermore, we use a special property of this quantity of delta Q to simplify the computation. The special property is the delta Q depends only on the total charge, Q, and not on the values taken by the various single ON charges, which are n alpha. So we just fix only one charge to Q, and this simplifies considerably the computation. What we actually compute, following the work of Badel, Cuomo, Rattazzi, and Monin, has been to compute the matrix element of the evolution operators, e to the minus ht, with h the Hamiltonian and t the cylinder time, in arbitrary state with total charge Q. At this point, taking the limit where we send the cylinder time to infinity, we can project out of this matrix element the energy of the ground state, which is related to the scaling dimension delta Q of the lowest lying operator with total charge Q. Very good. We just have a look to how this ground state look. All the details I will say about the computation. This is better visualized using complex fields variables, which can be defined as in the slide. And also for the first variable associated to the charge we fix, we can use polar fields, polar coordinates for the fields. And the ground state is the one shown in the slide where the radial mode of the first complex field take a wave. The angular mode is, as usual, proportional to the cylinder time, the chemical potential entering, and due to the cubic coupling, also the ON singlet eta acquire a non-trivial wave, even if it's an uncharged field. So the solution depends on three parameters, f, mu, and v, which are fixed by the equation you can see in the slide. In terms of this parameter, we can then compute the ground state energy, which gives the leading order of our expansion, as shown in the slide. So it depends on these three parameters, which are determined by the equation of motion. And the equation of motion at this point can be solved numerically or analytically in certain limit. It's interesting, for instance, to consider what we can call the small charge limit, where Q times epsilon is much smaller than 1. Actually, even if called this small charge limit, this can be misleading because the charge is still large, but it's not the larger parameter in our system. It's much smaller than 1 over epsilon. So it's say smaller of the other parameter for our system. And this is the result we obtain in the perturbative expansion for small q times epsilon, where I colored in red all the terms we can compare with the results of Jombie and Hyman. This is an infinite series of terms. We computed, of course, not all of them, but say quite a lot of them. And we showed that for all these terms, they match between the cubic description and the quartic description of this conformal field theory. So supporting the equivalence of the two descriptions of this conformal field theory. We can do the same also for the next reading order. This quite long, also boring computation, so we'll again not go into the details, but again we can consider the small charge regime, q times epsilon much smaller than 1, and again we found all the rare terms showing the slide, order by order, match between the cubic and the quartic description. Which is the moral of the story here? The point is that considering this type of double scaling limit, then it's possible to compare infinite series of terms between the two theories. And this has been done here for this particular case, but can be done in general for other, for instance, conjecture equivalence between two theories. And so these are useful tools to test dual description beyond the first few orders of perturbation theory. It's interesting also to analyze the what can call the large charge regime, where q times epsilon is much bigger than 1. In this case, we write our result in terms of the variable j, q equal n. This is shown in the slide. In this regime, the scaling dimension take the form predicted by the effective field theory approach. So, for instance, with non-integral power of the charge, here the scaling in 6 dimension is q to the 6 over 5. But we can note also the fact the scaling dimension in this limit is complex, as we already observed on the quartic side. And now we confirm this observation of the cubic side of the dual description. So we see that has to exist a critical value of the charge above which the scaling dimension becomes complex. Why is so is still fully to understand. Is, in my opinion, a very interesting question. To analyze even more deeper this issue, we use our result to compute this critical value of the charge. In particular, we compute the critical charge at the leading order in the epsilon expansion for both the quartic model in 4 plus epsilon dimension and the cubic model in 6 minus epsilon dimension. How we determine this critical value of the charge? Well, the point is that above the critical charge, there are no real solution to the equation of motion. Then we look for the value of the charge will allow for real solution to the saddle point equation. And this way we determine the critical charge. This is the result, which again, we write in terms of the variable j, so the ratio q over n. In particular, the blue line is the behavior we found for the critical charge at the leading order in the epsilon expansion in the cubic model in the equal 6 minus epsilon, which describe, of course, well the behavior near 6 dimension, but not well at all the behavior near 4 dimension as expected. The red line is the result we obtain for the quartic model in 4 plus epsilon dimension. Sorry, mistakes, should be 4 plus epsilon not 4 minus, at the leading order in epsilon, while the black dot is the numerical estimation shown before, which has been done in the quartic model, and a leading order in the 1/n expansion, actually in double scaling limit, large n and large charge, by Jombie and Diamond. So there are still many things to understand on this issue. For here we see that the behavior in general is qualitatively well described to the fact to have the free theory on both sides, in d equals 6 and d equals 4, but there is still a lot to understand. And with this, I conclude, and I thank you all for attention and for organizing this workshop. Thank you.
Thank you very much. Are there questions for the speaker?
Hi, I have a question. So when JC is much less than 1, when n is much larger than the charge, so we have this perturbative expression for the operator dimension, right? Should I think of it as having a very small imaginary parts to the dimension, or is it exactly 0?
The point is a good question. The point is, yes, I can have a closed form and expand in the true regime. If I expand it in the perturbative, let's say, regime, I don't see any complex. The perturbative expansion is real order by order.
Yeah, yeah.
On the other hand, it's clear that the perturbative series has a finite radius of convergence, which in this case appears to be in the middle between the small charge and the large charge regime. So one cannot smoothly interconnect the two regime. One can wonder if the appearance of complex anomalous dimension is simply a consequence to push the resummation of the perturbative results beyond this radius of convergence, or if we are really talking about a real physical effect. This is, the main open question about this point.
I see. Is there any numerical computation to prove or disprove this? Okay, even at q equals to 1.
Numerical computation, I'm not aware of any of them.
Yeah, okay. Okay. Bootstrap doesn't usually work.
Can be.
No unitary. Yeah. I see. Okay.
Yes, one may try to consider very large n when the theory is almost unitary, but I don't know how much, because at this point one would still feel also the instanton effects, which is not clear how are related to this. One may consider the effective field theory approach directly in 5 dimensions, and may try to compute the coefficient of the large charge expansion on lattice. But this, in the theory non-unitary, I don't know if this is possible at all, or there are